that's open already. Can you all see the screen that says longitudinal shear stress?
Yes.
Yeah, I can see it.
Yes.
Awesome. All right. So this is simply what we're going to try to talk about today. And I'm going to try to make it brief because I don't want today to be a really, serious lecture. I just wanted, us all to just kind of be a little comfortable. I'm sure you all are probably going to have additional lectures today, I would assume, with other professors, and they're going to probably use Zoom. But what I want to do is use Zoom as much as I can using the live the live feed, I guess. So try to do my lectures live, but we might get into some issues when maybe I'm not able to do a live lecture, or we having issues with connections, and I might at that point maybe do a pre-recorded lecture and then send that to you guys for you all to watch. I'm not sure how we're going to do exams at this point yet. I'm still trying to think through that. But anybody get suggestions or I mean, let me ask this first. Would you all prefer the live lectures or pre-recorded lecture?
I like the live ones personally. That way we can ask questions as it goes.
Got you. At the point that you have the question, you're able to ask it right away.
Yep.
I think it would be great to also just record these and upload them somewhere. So if we do initially struggle, we can just go back and look at it again.
Yeah, that'd be really nice.
Got you. I think this has been recorded. Let me see if I can verify that.
I'm seeing a recording little button up in the upper left corner.
And it looks like it is recording, right? Yeah. Like recording on this computer. So yes, it is recording. And I'll try to, what I probably will do is maybe go ahead, after I do get the recording, go ahead and post that on Moodle anyway. So at least if y'all need to go back on something, you'll have the recording as well. If that'll help, I think it would. All right, so longitudinal shear stress. Our learning objectives for today is maybe really just that first one, right? Just to be able to explain the concepts of horizontal shear. I know we've talked about shear. You've all drawn shear diagrams. You've all looked at maybe a cross-section of a beam or cross-section of something, an object, a member, where we looked at normal stresses, and we've also looked at shear stresses along that cross-section, right? If you remember, I think that one of the last things that we did, we cut a beam section and we were able to look at the normal stress, right, on the beam, the moment, and also the shear stress, right? We had those three external forces, if you would, right, acting on that member when you cut the section. For the most part, the normal force has been zero, I think, because there's no, unless we have a fixed end where we might have a lateral or horizontal resistance, then that normal force would exist. But if not, if we just have simple supports, that horizontal force would be zero internally. But now what we're going to look at is, instead of looking at the shear force along the cross-section, right, or parallel to that cross-section, we're going to look at the shear force along the length of that beam. And so I'm probably going to try to turn my video off here because I need to write on my computer and I got to turn the screen over. So I'm going to turn my screen over. So y'all are probably going to try to see maybe my ceiling if I don't turn the video off. But what I'm talking about is shear stress on a horizontal surface. So, and of course now my pen is right. It's all out earlier and it was working just fine. Oh, I'm having trouble with the pen. All right, give me 1 minute here, see if I can make this. Hey, I like that. Somebody's playing good music. All right, so we're looking at shear stress, right? Shear stress. Can you all see me right?
Yep.
Yep.
Okay, good deal.
Yep.
So shear stress on horizontal surface. And by this, basically what I mean is if I draw a beam, and let's say that beam is again simply supported with a pinch support and a roll support, and I have some external forces. I'll just put a point load there. I'm gonna put another point load there, and let's just say this is a distributed force, and I'm gonna make it just some not a uniform distribution, basically. Right? Let's say we have something like this, and I just want to draw this straight. There. What I'm actually looking when I say my horizontal surface, I'm saying if I look at maybe a section, I'm going to do it underneath the distributed load. Let's just say we're looking at maybe a section here, right? That small section. And if I try to draw that section and look at the forces acting on that, or the stresses and forces acting on that section, let me draw that here. Sorry, that should be a straight line. So that's basically that small section that I showed on the beam, on the longitudinal section of the beam, right? Where did we say the maximum normal stress occurs on a beam?
The furthest distance from the center.
Further distance from the center, or from
The center line.
Right, the neutral axis, right?
Right.
So in essence, at the top, for example, let's say we have, let me put that in red. So my stress distribution might look like this for this section. Everybody agrees here? Right, so this is stress, and let me call this C and D. So this is D, so I'm gonna call this stress at D. But I'm actually trying to draw forces, right? Not stress. It's a force distribution. So therefore, this is gonna be times dA, right? We know stress is equal to that force or load over the area. So therefore, my stress is my force is the stress times the area. And so therefore, since I have a small area going from this point into the page, right, that would be my dA, right? So I have my stress times dA. And since the top of the beam has the higher stress, so therefore the higher force actually acting on it. So therefore it's sigma d dA, but it will be higher at the top and it'll start declining as you go down into the beam, right? So that's along this point of the beam right here. And I expect to see the same on this side. So I would have a distribution that looks like that as well. And this will be my stress at C times dA. Right? At the top of the beam, since this is the top, I would have this non-linear distribution. And so I'm gonna just kind of draw it like this maybe. Let me put some kind of funky line to it there. Right? So those are the forces, right, that we can say for sure that are on the beam, on that little member, little portion that I'm considering. What about this bottom section? Would you all say that there might be a force acting there?
Yeah, it would depend on basically how far away it is from the center line, right?
Yeah, so, okay, so say I cut this section out, right? Or not cut it out, but I'm trying to look internally into that section. I know I have this acting at the top. I know I have this force acting this way on the right side and on the left side. But if you think about those forces, right, acting on the left and right of that beam, and at the top it's larger, at the bottom it's getting smaller as I go into the beam to that neutral axis where it could be zero, for example. So I should expect that there is some force acting along that face that would be in either the left direction or the right direction, right? And let's call that delta H, right? So I'm just trying to paint that picture that there is longitudinal forces, shear forces that are acting internally on a section or any section of that beam, right? So you expect to see some force acting along the longitudinal surface of that beam. And if we say this, let's call it delta X, that distance here. So just a small change in the horizontal direction, right? And we know this is C, we know that's D.
Wouldn't there be a normal force acting back up on it from the bottom?
So this beam, we can say maybe it's in bending, right? So I'm only looking at the internal forces, right? And there's no support at the bottom.
Oh, okay.
Right? So because of that, what that beam is actually gonna experience is, let's say if you take a stack of papers, right? And you put those forces on there and you try to put that stack of paper maybe in bending because of those forces, those external forces. And you put it in bending, that stack's gonna wanna move. For example, say you bend it down, for example, like concave up, so the beam is bending down or the stack of paper is bending down, so it have that concave up shape. If you look at the edges of those papers, you're gonna probably see a shift, right?
Yeah.
The bottom, yeah, so that's kind of what we're looking at. If that paper is trying to shift, therefore there are those horizontal forces, longitudinal forces acting within each of those papers, right?
Yeah, that
And
makes sense.
that's right, that's what this is. So that's what we'll see, right? So let me go through a quick derivation here. So if I look at this example that I showed here, and I want to sum forces in the X equals 0, and let's just say that is positive. So if I look at my forces, delta H, right? We have delta H. And I'm gonna say minus because now I want to look at this right here, the sigma CDA. So, well, let me say plus first. But since that force is going in the other direction, it'll be a minus. And I'm going to use an integral for it, right? Because it's non-uniform. So it'll be sigma c dA, right? And I want to integrate with respect to the area, right? And then I go plus on the right side, we would have integral of sigma d dA with respect to the area, right? So these are all the forces that are acting in that horizontal direction or the x direction. And of course, we can equate that to 0. So just using that equation, delta H equals, delta H minus integral of A for beam bending. What is sigma? Right? Sigma equals what?
M over S.
M over S, right? M over S, or My over I, or MC over I, right? But since we're looking at forces along, there's a not necessarily just at the top, I'm going to use Y, right? So it'll be sigma is negative My over I. So therefore, this negative My over I dA plus integral to A negative M, I should call this MC, and call this MD, Y over I. And equate that to 0. So delta H, if I move all that over, that's minus, minus, but if I move it over, it still be minus. So that's minus MC over I. And dA is just, let's see, so YDA, that's what I'm left with. Right, because the moment is going to be constant, the I is going to be constant, so I can take those out. And then I move this negative. Ooh, I don't know what I did there. A lot of stuff just went away. I can go back. I don't know what just happened. All right, I just write it again. Y over dA equals 0. All right, so I have MC over I integral Y dA plus MD over I integral Y dA equals 0. All right. Now, I wanted to put it in this form because I'm hoping you all remember, again, if I come over here, this was M over S equals MY over I. I'm hoping you all remember when we talked about bending stresses, right? We use MY over I or MC over I, right? And therefore, if I take the moment out of that, it's going to be negative stress times I over C, right? And therefore, we're going to have, let's see, negative the stress over C in I. So I'm working backwards here, would be Y squared dA. Do you remember that? Where our moment of inertia was the second moment of area. Do you remember the term Y squared, integral of Y squared dA? Anyone? Nobody remember that? When we would derive in bending moment, bending stress?
Yeah, I don't really remember that.
Okay. Okay, I guess it's been a few weeks. but we talked about, remember we first looked at polar moment of inertia when we did torsion, right? It was integral of r squared dA. Then when we got to looking at bending stresses, we defined I as integral of y squared dA. So I is called a second moment of area with respect to the neutral axis, right? But here we got integral of y dA, right? So y dA, let me put that in red here, is a term that we usually represent as Q, right? And that's the first moment of area. Right, and that's with respect to the neutral axis. Right, so it's an area that's above or below. The neutral axis. Right, I just kind of wanted to put it into that form so y'all can maybe see somewhat of a relationship from a second moment area, which is I, that moment of inertia. Now we're talking about the first moment of area, which we call Q. So with that in mind, let's look at, so if I look at this equation again, right, and for let me see, if I take y dA out, I'll have md minus mc, right? So md, put it in black, md minus mc, let me actually write that out for you guys so y'all can see what I mean. All right, so delta H equals to be md minus mc over I integral of y dA. Right, so I just simplify this equation above. Right, if we take y dA out, you have md over I minus mc over I, which is md minus mc over I. Right, so now I just want to look at md minus mc. It's just a change in the moment going from C to D. Right, if we go back up to the beam, it's just a change in the moment going from here to here. Right, so we call it change in moment, delta M. I can also write that as the derivative of M with respect to X, right, delta X. Right, okay, so if I write it in this form, the derivative of M with respect to X, what is that? If you go back to the shear and bend and shear and moment diagrams, remember trying to get the moment diagram, we looked at the area under the shear diagram. So in essence, the integral of the shear is the moment. So if I take the derivative of the moment, what is that?
Shear.
It's the shear, exactly, yes. So basically moment minus MC is equal to V, which is the shear that we've been talking about all along. That's the shear along the cross section, dx, delta x, right? So therefore I can write my delta H going back to that first equation as V delta x, delta x over I, multiply now by my Q, right? So MD minus MC, and I did it again. I don't know what is going on. Stop. All right, I guess I'll write it again. V delta X. Let me just write it. I can go back more than that. So delta H equals V delta X over I times Q. Right? So MD minus MC is V delta X. V delta X over I, and my integral of YDA is now Q. Right? So in essence, I can write it as VQ over I delta X. Right? So therefore, if I look at an average shear stress, right? So now I'm looking at shear stress. So I can write my shear stress as tau. If I know a longitudinal shear force, delta H, right? If delta H is a shear force, what would be the shear stress? What is stress?
Force over area.
Force over area, right? So the shear stress would be shear force over area, right? So therefore, my shear stress would be my shear force, delta H, divided by some small change in area, delta A, right? I can therefore write this as delta H, which is VQ over I delta X over my delta A, right, which would be T delta X. All right, so let's go back and so I can try to explain where I get T delta X from, right? So if I go back up here, right, I'm looking at the area right here underneath that beam, that section that I'm considering, right? So it's delta X times a thickness into the board, into the paper, right? So if I'm looking at the underside of that beam, if you would, of that section, it would be delta H times some thickness of that beam. And that's where T is, right? So T, maybe if I indicate what T is here, is thickness of beam portion. Right? So therefore, we went all through that derivation just to get you this is equal to VQ over IT. Right? So your shear stress in your beam that's acting horizontally, right, at any point in that beam is equal to the shear force V, right, which we know how to determine. We can draw a shear diagram. We're able to get V at any point along the beam. And now we know this new term Q, which is just an area, right? And that area could be above or below the neutral axis. And we'll talk a little more about that in a minute, but divided by I over T, right? So basically we went all through that process just to get this equation that shear force is equal to VQ over IT. And this is a very good equation to know. So y'all make sure you all remember that equation. Now, the derivation was just to help you understand how you get the equation. I'm not gonna try to bring back the derivation or make you all try to derive it for an exam or anything like that. It's just so you all can try to understand where that equation came from, right? I just didn't want to give you all the equation directly. I think you all should be able to understand that process using derivatives and integrals to be able to come up with shear stress now equals VQ over IT. So I think the only thing that we really need to talk about is really how do I get Q, right? Because you know how to get V, you know how to calculate I. T is just the thickness of the beam, and that could change if the beam has, if it's not a prismatic beam, if it's a different cross section, right, throughout the length of it, that T could change. But you just got to know that you have a different cross section at different points along the beam. And for wherever you need to calculate shear stress, you use that thickness at that point, right? So I'm going to try to get maybe one more thing across to you guys, and let's quickly talk about the first moment of area. First moment of area. Right, so you all know Q now is the first moment. That's with respect to the neutral axis of an area above or below the point at which shear stress is calculated. All right. So, let's see. I think actually I only really get 2 more minutes. So what I'm going to do is I'm going to stop here, and we're going to continue from here on Wednesday. But at this point, I don't know what is going on. I keep losing stuff right here. But do you all have any questions that might be lingering? All right. Any other questions? I certainly don't want to keep you all here. I mean, we can talk, but if you need to go, if you got another class, good luck, and maybe let me know how it goes.
All right, will do.
All right, guys. Well, thank you very much. I hope this all went okay with you guys, and we're gonna keep trying to do this. But again, let's keep this communication line open. If you think I need to do something different, again, just let me know. Okay.
All right. Thank you. Have
Awesome.
a good day.
You too. Thank you, guys.
Yep.
Thanks.
Mhm.